YouTube? Oh, that's exciting.
Yes. Yeah.
So we need to behave now. We're on YouTube. Yes, Werner was explaining the dynamics of this examination.
Okay.
So, yeah. So, hi Rosa, my name is Juan Yus. So, yeah.
Hi. Nice to meet you.
Nice to meet you too. Oh wait, I have an issue here. I opened YouTube, so I'm listening to my voice with delay.
Don't do that.
Yeah.
Okay, I clear myself. That's good. Yes, so at least we can wait for 2 more minutes. But the idea is I'll be in charge. I'm on the committee. And so Patricio will present the thesis, and then we'll have time for questions, and then we'll go to a separate breakout room here in Zoom to discuss and to evaluate both the thesis document and also the presentation that Patricio will do. So that's basically what we're going to do today. I don't know if you have any question, Naoi or Rosa?
No, I guess that after he make the presentation, we will have to ask question, no?
Yes,
we
yes.
can discuss with him.
Yes.
Okay.
Yes.
If I may say something, I also checking at the YouTube channel, see if anyone in the streaming audience have a questions. I can reply to Patricio.
Yes,
good.
yes. I was going to ask also that if you're going to take the questions or comments from the YouTube, you can do that. Excellent.
Yes.
I have advertised this defense in my group, so I don't know if, at least I think that Juan Carlos Lozada is going to be connected, and I don't know if other students will do or not.
Okay.
That's great. That's great.
We have 9 people already in the streaming.
The streaming group.
And can you see who they are?
No.
Oh, okay. Okay, so hello to people in YouTube. So I think we're ready. Can we start, you think, Werner, Patricio?
Yep. Yes, of course.
Okay, so I will say hi to Felipe. Hola, Felipe. Thanks for connecting. Felipe is not officially part of the committee, but he was invited, of course, to this examination. And it's very common for us to let people ask questions. So Felipe is very invited to ask questions to this, to poor Patricio. It's here. Okay, so we will start. Thanks everybody to being here today. Thanks to people connecting to YouTube also in this special month that are here with the pandemic. So today we're here to see the presentation, the thesis defense of Patricio Olivares. I'd like first to thank especially Professor Rosa Benito from Universidad Técnica de Madrid in Spain, and that is part of the committee, and also Professor Naoya Fujiwara from Tohoku University in Japan. And thanks a lot for accepting being part of the committee and evaluating the thesis and defense. Also, Werner Kreisel is the thesis director of Patricio, and my name is Juan Yus. I'm part of the electronic engineering department here at Santa Maria University, and I'm the head of this committee today. Okay, so thanks Werner also for inviting me to be part of the committee. So Patricio will present his work today, and then we will have time for questions from the committee first, and then we will look at the questions or comments on YouTube and also here, Felipe or Professor Vallejos, Ronnie Vallejos, probably may also connect later. So Patricio will present today his work on dynamical impacts of decoupling in a model of interactive infectious diseases. So Patricio, it's all yours.
Thank you very much. I will start sharing my screen. So please let me know if you can see it right now.
Perfect.
Sí, es perfecto.
Thank you. Thank you very much. Okay, so I will start this presentation. Good morning, good afternoon, and good evening to all the members of the committee. I will start my PhD thesis defense that is called Dynamical Impacts of the Coupling in a Model of Interactive Infectious Disease. So in this presentation, we will talk and we'll discuss about the temporal characteristic of one disease, which we will try to describe how these temporal characteristics, as a time scale, for example, can affect the behavior of another disease when both of them are affecting the same population. So let me start discussing about the importance for the importance on make research in epidemic spreading disease. So we already know a little bit examples that have been occurring the last few years. For example, the Ebola viral disease with more than 3,500 of cases in West Africa, or the Zika virus with a total of 29,000 of people infected in French Polynesia just in 2014. But of course, the trending topic right now in this area is the pandemic occurring right now, the COVID-19 virus, with in the last report that I could see, with more than 35 million of cases around the world. So it's a pretty serious topic to study right now. So the question that we can make to ourselves is, when we are facing a new epidemic disease, what can we do to try to attack this problem? So the first answer to this question could be make some treatment, some medical treatment to the epidemic in order to attack the symptoms and try to help the people that are infected from the disease. But we can also make some kind of prevention. So for example, in this area, we can start talking about vaccines, for example. But there is another solution that is try to understand the behavior of the disease. And if we understand in a pretty good way how the disease behaves, we can take some decisions in order to mitigate the effect from the disease in the population. So in this case, we will start talking about mathematical modeling of from diseases, and we'll see what can discuss from this epidemic behavior. So let's start talking about one of the most popular epidemic models, that is the called SIR model. The SIR model has three states where each people in the population can be in one of those three states. The first one is the called S state, that means susceptible. That means that one person at a certain time can be susceptible of being infected from the disease. The second one is the called I state, that is the infected state. That means that, of course, the person is infected at a certain time. And the R state, that is the recovered state. That means that a certain person is recovered after being infected from the disease. And the movements from one state to another are given by those rates given from the parameters beta and gamma. One of them is the infection rate. That means the number of people that are infected from the population per unit of time. And the gamma parameter is the recovery rate. That means how much people are recovering from the disease per unit of time when after being infected. So this model can be interpreted by this set of differential equations for a fixed population of size n that link all the states and its rates of propagation in that case. So we can tell that if we make a summation from all the states, that means that all the people in the population must be in one of the three states. So of course, if we make the summation of these three states, we will have the total number of the population, in this case n. And the flow of the different states, if we make the summation, in this case, we will have a total 0, because each person moving from one state must be in another state. So the total flow between the states must be 0. So even that could be very interesting to talk about a fixed size population of size n. In this presentation, we will talk about proportions. So we can modify the original equation just dividing all the terms by n. And in this case, we will talk about the proportion of being susceptible, infected, and recovery from each state. So the notation that we will use here will be S square brackets for the proportion of people being susceptible, I square bracket to the proportion of people being infected, and R square bracket for the proportion of people being recovered. So from this part of the presentation and so on, I will talk just by S, I, and R in the next slides. So in this case, because we are talking about proportion of people, if we make the same summation, instead of being the total number of people in the population, that means n, the summation of all the three states will be 1, and the total flow will be the same, will be 0 in this format of the equation. So if we see the solve of the equations seen as a plot, as a graph, this is a very common SIR model evaluation of the model. So we have for the number of people susceptible in this blue line, the number of people recover, the proportion, sorry, of people recover as a green line, and infected, the proportion of people infected as a red line. So in this case, we can see that the number of people susceptible always will be decreasing, and the number of people recovery will be always increasing because of the effect of people start going from susceptible to infected and from infected to recovery, okay? So from this point, we will try to describe with more detail this model and try to specify the temporal characteristic of the SIR model. So let me define some additional terms. We will talk in this presentation of the reproduction number, that is this R0 term here, and it's defined as the rate between the infection rate and the recovery rate. The characteristic of this term is that if the result of the division between the infection rate and the recovery rate is bigger than 1, that of course means that the number of people being infected from the disease is more than the number of people being recovered from the disease. So of course, in that case, the epidemic spreading disease will start an outbreak. So the number of people, the proportion of people infected will start increasing until it reaches a max point, and from that point will start decreasing. But if we have a reproduction number equal or lower than 1, that means that the recovery rate is bigger than the infection rate, and there is more people being recovering from disease than infected from the disease. So in that case, we will never have an increase in the number of the infected people. Okay, so now let's start talking about some temporal characteristic of the SIR model. So let me define some additional terms to try to understand the time scale in this case. Let's define Imax as the maximum number of people being infected in the total time of the disease. And tau will be the specific time when Imax occurs. So you can see in this graph the relation between Imax and this tau time. And we will call a disease as a fast disease when this tau time is small. So you will see that tau will be very near to the origin of the time scale, the time axis. And we will call a fast disease when this occurs. In the other hand, when we have a big tau, we will call this case a slow disease. So when the tau time is very big, so it will be in the right hand of the time axis. That means that the disease take more time to appear and present this effect. So we will call this as a slow disease. Additionally, we will talk about the prevalence, that is this term from here. That is the final size of the infection. That means that if we wait enough time, all the people being infected from the total amount of time of the disease in some moment will be as a recover. So if we wait enough time in order to be recovered, this state will represent the total number of people being infected in the life of the disease. Okay. So from that point, we can make some evaluation. What is the relation between the reproduction number and the time scale from a specific disease? So in this example, we have 3 different diseases, each one defined with its own time scale, defined by these tau values, but all of them have one characteristic in common, that is defined by the same reproduction number. Okay, so and this occurs because we choose beta and gamma parameters in order that the division between them gave us the same reproduction number, in this example 1.1. Okay, so we can define different diseases with different time scale that all of them has the same reproduction number. Okay, but even that this different disease has different time scale, the prevalence in this case will be the same as we can see in the proportion of people being recovered. So if we wait enough time for all diseases to be complete, all of them will have the same amount of people infected. So that is the context from the SIR model. So because we are trying to discuss about interaction between 2 diseases in this research, let's start talking about the state of art and what are the research made in this area. So I want to make some examples in order to try to show you that cases of interaction between diseases exist in real life. So for example, there exists the case of meningococcal disease and influenza virus that some research has found a strong relation between an increase in the number of people getting infected from influenza and an increase in the number of people getting infected from meningococcal disease. And another interesting case is what caused the dengue hemorrhagic fever. So in this case, when in a certain subject, it's infected by 2 or more strains from dengue disease, that can produce the dengue hemorrhagic fever. That means that in a certain subject, there are interacting 2 or more strains of dengue that can produce the dengue hemorrhagic fever. So we can start asking what are the models that has been used in order to understand these epidemic diseases. So one of the initial attempts to try to model this kind of interaction between diseases are models that consider competition between diseases. That means that you can only be infected from one disease or another disease, but not of them, both of them at the same time. So for example, one of the most popular models that represent this kind of model is the SI1, I2S model. That means that a certain subject of the population can be in the state susceptible or be in the state I1, that means infected by disease 1, or in the state I2, that means infected by disease 2. Okay, so this was one of the first attempts to try to model this disease. So in the following years, multiple attempts to try to define other kind of interactions were made. One of them is try to set compartmental disease models to try to define cooperation between diseases. That means that if you have an increase from one disease, you can have an increase from the other disease too. So one of the models that can represent that behavior is the show here, that could be similar to the model that we will use in this research, but has a lot of simplification and assumptions that are the behavior of both diseases is almost the same. So they have a symmetric behavior in this case that is not considered in our research. And in the last attempts to try to identify multiple kinds of interaction, there has been an increase in the use of multi-layer networks model where each disease is represented as a layer in the network. And you can see here interactions between diseases as links between layers. And of course, you have interactions inside the process of an epidemic as links between nodes here. And this is represented as a fourth order tensor using multilinear algebra in this case. So considering the state of art, let's start talking about our proposal. This is the state diagram of our model that we will discuss in this moment. So here we have 9 different states. So each person can be in one of these 9 different states. And the notation here is related for the state for each individual for each one of the diseases. For example, the state SS means that the one person can be susceptible of disease 1 and at the same time is susceptible of disease 2. Okay? So the same goes for all the states. For example, the state RI means that a certain person is recovered from disease 1 but infected from disease 2 at the same time. Okay? So at the same way as we see in the SIR original model, we have to define infection rates. So we have, for one hand, the infection rate for disease 1 that we will call beta 1, and the disease, the infection rate from disease 2, beta 2, and the same goes for the recovery rates gamma 1, gamma 1, and gamma 2 for the recovery rates from disease 1 and disease 2 respectively. But the modification here will be what happened when you are infected from both diseases at the same time. So the assumption that we made is that when you are infected from both diseases, you can experiment a different behavior on how disease behaves in this case. So that change in the behavior will be represented as this new infection and recovery rate that will be called beta 1 int, that from interaction, beta 2 int, gamma 1 int, and gamma 2 int. So when you are infected from both diseases, you will have a new infection rates for both diseases and a new recovery rate for both diseases. Okay, so if we want, for example, try to understand how much people each state, but for only one of the disease, we can make a summation of the different terms that we define in the diagram state. So for example, if we want to know how much people is in the S1 state, we have only to make a summation from all the terms that include the S state for disease 1. So for example, the proportion of people being infected from, being susceptible from disease 1 will be the summation of the state SS, because this state include the state of susceptible of being susceptible of disease 1, the state SI that include the state susceptible of disease 1, and the state SR of being susceptible of disease 1. The same goes for each different state. Okay. So as we saw in the SIR model, we have also defined a set of differential equations that represent the behavior of those different states represented in the diagram state of the model, that made a link between how different states behaves and how the infection rates make modification on these states. Okay. So in order to better understand this proposal model, we'll make some additional definitions at the same we saw in the SIR model. So in this case, we want to know what is the effect from one disease in the behavior of another when we make some change on it. Okay, so let's start with some definitions. In this example, we have one disease that is disease 1, in this case, as a green line, and we have disease 2 as a blue line. In both cases, we are representing this disease as independent. So there is no interaction in this case. Okay, so when we don't have interaction, we will add the term supra-zero in order to identify that the term that we are talking about is the case of independence. So in this case, disease 1 has I1 max number of people infected in the maximum moment, and it's related with tau10 as the peak time of this disease. And in the independent case of disease 2, we will have I20 max number of people infected and the maximum moment, and will be related with tau20 peak time. Okay, so the question is how the disease 1 can affect disease 2. So we will have in the following evaluations that, for example, here, in this case, we have in black line how the disease 2 changed its behavior. So we will call this new behavior in the maximum number of people getting infected as I2 max. And the new related peak time for the disease will be tau2. Okay, so we will have defined all this term for the interactive case. And of course, we will have to define the prevalence for each one of the diseases, as we can see here. So I want to show you once again that when we are talking about independent case, we will add the term supra-zero in order to identify the independence in that case. So in this specific research, we will talk about the unidirectional couples. So because there are so many parameters that we can modify, we will only study what happens when one disease affects the other for all the possible kind of interactions. So let's define some terms in order to understand this behavior. So for example, if we choose the parameters beta int and gamma int for one disease equal to the parameters beta I in this case and gamma I, we will have, because of the equation that we define, that will mean that disease I in this case will be totally independent from the other disease. So the states SI, II, and RI will be the same as the independent case, as we can see here. And another characteristic of this model is that it's invariant under transformation. That means that if we change the temporal characteristic of the disease, for example, dividing these terms by a constant, a positive constant k, we will have always the same number of people infected in the long term. So the prevalence will be the same, even we are changing the temporal characteristic of the disease. Okay, so because we are studying unidirectional coupling, we will change only one parameter from this model, and that parameter will be gamma 2 int. So if we change gamma 2 int, we will have an effect in the behavior for disease 2 from the behavior from disease 1. And how are these changes? If we define gamma 2 int smaller than gamma 2, we will have a cooperative case. That means if we are having a gamma 2 int value smaller, the people is getting more time to being recovered. So people take more time to recover from the disease. So they have more time to infect more people. Okay, so that will get an increasing number of people getting infected, and that will be that we call it a cooperative behavior. In the other hand, if we define gamma 2 int bigger than gamma 2, people will be recovering more, will be recovering faster, and that will produce that people will have less time to infect new people. So we will call this behavior as competitive. Okay, and of course, if we define gamma 2 int equal to gamma 2, we will have the independent case, because gamma 2 int will be the only parameters that we will change. Okay, so the question here is, if we make modification in the temporal characteristics of disease 1, what kind of behavior will produce in disease 2 when we change the parameter gamma 2 in this case, okay? So the temporal characteristic of disease 1 will be defined by its tau 1. So if we change tau 1, the effect on disease 2 will depend if we are talking about competition or cooperation, and of course in the independent case will be not won't be any kind of interaction, okay? So if we are talking about competition, if we define tau 1, the temporal characteristic of disease 1, smaller than tau 2, that means that disease 1 is faster than disease 2. Because of the competition, the disease 2 will try to move away from disease 1. So that means that disease 2 will be, the peak time will appear later, so disease 2 will be slower in this case. In the other hand, if we define tau 1 bigger than tau 2, that means disease 1 will be slower than disease 2. Once again, disease 2 will try to move away from disease 1 because of the competition, so we'll start getting faster in this case. So in this case, tau 2 will be smaller than the tau 2 getting in the independent case, so the disease will be faster. And if we are talking in the case of cooperation, if we define tau 1, the peak time of disease 1, smaller than disease 2, that means faster, in the case of cooperation, both diseases will try to move closer, okay? So in this case, tau 2, the peak time of disease 2, will appear earlier, so will be faster. And if we define tau 1 bigger than tau 2, that means disease 1 getting slower than disease 2, we will have that, once again, because of the cooperation, both diseases will try to move closer. So tau 2 will appear later and will be slower, okay? So that is what we get from the model and the equation. So in order to get the results of this, we make some evaluations, some numerical results that we have here. And I will try to explain the methodology here. We use LSODA, that is a solver for different, as a set of differential equations in order to produce the numerical results. And we define some parameters in order to have one example of this interaction. We define the delta time as 0.002 in this case. And we define, as we talked about earlier, that disease 1 will be totally independent from disease 2. Not in the other hand, disease 2 will have some change in its behavior because of disease 1. So in order to have this independence, we define these parameters, and we define the reproduction number equal to 1.35. So because it is bigger than 1, this will produce an outbreak, okay? And for disease 2, we will define 3 different scenarios. We will define the cooperation, defining gamma 2 as 0.3, because in this case, gamma 2 is equal to 5.5. In the independence case will be 5.5, because gamma 2 must be equal to gamma 2. And in the competition case, we will define gamma 2 equal to 19.5 in this case, in order to get a competitive behavior. And for other parameters, we will define beta 2 equal to beta 2 equal to 6.15. So what are the results? Of course, in the independent case, even we change the temporal characteristic of disease 1, we don't have any change in the behavior of disease 2 as we can see here, because we define the independent case for this result. But if we are talking about cooperative case, as we can see, as disease 1 is getting closer as for the time scale of disease 2, the original case of disease 2, the number of people getting infected start increasing, and the temporal characteristic of disease 2, meaning the peak time of the disease 2, try to get in closer to disease 1 in this case, okay? And the competitive case, we have the opposite behavior. as the disease 1 is getting closer to the temporal, the peak time of disease 1, in this case, the number of people infected start to decrease. And also the peak time of disease 2 is getting away from disease 1. So we here, using this model, and also because of the numerical results, we can see that just by modifying temporal characteristics of disease 1, we can also modify the behavior of another disease because of these interactions, okay? So another interesting result that we found in this research is the appearance of a secondary outbreak. So there are some conditions that produce a secondary outbreak in this case. The first one that we found is when disease 2 is faster than disease 1, or in other words, when disease 1 is much slower than disease 2, that can produce a secondary outbreak only in the cooperative case. But in the cooperation that is defined with gamma 2in being very much smaller than the original gamma 2 for the independent case. So as we can see in this example, we have a disease 2 with its normal peak value here, but only because of the interaction with disease 1, there appear a secondary outbreak. So because of the results of our model, the model predicts if we have a specific condition in this case, we can make another disease because of the interaction produce a secondary outbreak just because there exists interaction with another disease, okay? So finally, let's start talking about the dependence of the model with the parameters in a more general way. So in order to understand the results, let's start talking about the dependence between the beta 1 value of the disease 1 and the temporal characteristic of the disease 1 defined by tau 1. So as we can see here, there is a strong correlation between tau 1 and beta 1, given big values of beta 1 that will produce a faster disease because tau 1 will be smaller. And when we define a small beta 1, that will produce a slower disease because we will have a bigger tau 1 values. So the question here is modifying the temporal characteristic of disease 1, how it changed the behavior of disease 2. So let's start talking about the prevalence case, that is this plot from here. So here we have 3 different cases of selecting parameters for gamma 2int. This line here in the middle represents the independent case. So the left side of this plot mean the cooperative case, and the right side of this plot mean the competitive case. So as we can see here, each point of the left side is bigger than in the case of independence, okay? And each point in the right side, that means the competitive case, is smaller because we are decreasing in the competitive case the number of people getting infected for the disease 2. But how it changed the temporal characteristic of disease 2, we can see it here. So we have in the cooperative case defined by the left side of this graph, we have that for big values of beta 1, remember that a big value of beta 1 represents a faster disease 1, that will produce that disease 1 is getting tau 2 values getting smaller, so that will produce a faster disease 2 in this case. And with small beta 1 values, that means a slower disease, that will produce also a slower disease 2 in this case. And in the competitive case, we have the exactly opposite case. Bigger beta 1 values will produce a slower disease, and smaller beta 1 values will produce a faster disease, okay? So in order to see this graph more clearly, we take some points, specific points from this evaluation, the one from the cooperative case, one from the competitive case, and the independent case, and plot some additional graph. So as we can see here, we have in the right side the prevalence, and in the left side the temporal characteristic of disease 2. So the tau2 value, the time scale of disease 2, will change depending if we are talking about cooperation, competition, or the independent case. Of course, in the independent case, tau2 value doesn't change at all. But if we start increasing, we start with small values of beta 1 for the cooperative case. In this case, the disease start getting slower, but as we start increasing beta 1 value, the disease start getting faster and faster, okay? And the opposite behavior is given by the competitive case. So we start with a faster disease, and as we start increasing beta 1 value, the disease 2 is getting slower in this case. But because of the secondary outbreak, and we can see it here clearly, in the cooperative case, when we define a gamma twin very small, there start to appear in the secondary outbreak. So the prevalence in this case start to increase for very small values of beta 1, okay? And from that point, it started the behavior that we were discussing earlier. So the number of people getting infected start to increase when we define the temporal characteristic of both disease very similar, and when the disease 1 start getting away from disease 2, because a bigger beta 1 value, the number of people will get infected also decrease, okay? And the opposite behavior for competition. So for small beta 1 values, we will have almost no interaction. And as we start increasing beta 1 value and the temporal characteristic of both disease start getting very close together, we have a bigger decrease in the number of people infected by disease 2. And later, there is no effect at all when we define a very big beta 1 value. So that are the results that we obtain in our work. I want to finish with some conclusion and future works. We define a compartmental model that is capable to not only define interaction as competition or cooperations, but all the possible cases. So we use this model to define also competition or cooperation between diseases, or even the independent case. We found that time scale is an important factor when we are talking about interaction between diseases. And we found also certain conditions that can produce a secondary outbreak because only interaction. As a future work, we are expecting to include more diseases, start talking about 3 or more diseases in the interactive model, maybe include the network configuration, the network of contacts between individuals in certain population, or even we can start including more compartmentals, like for example, start talking about vaccination, or for example, death states, and try to include it to our model and see what are the new results of this inclusion. So thank you for your attention and for seeing this presentation.
Well, thanks, Patricio, for your presentation. I guess there's a
sorry, of course, there is the citations.
Of course, doesn't matter.
Yeah.
So we can clap here in Zoom at least. Yeah.
Yeah.
So now we go into the section where the committee will ask questions. So I would like first to invite Rosa to ask questions to Patricio, please.
Okay. Hello. Well, thank you, Patricio, for your presentation that has been very clear and concise. And I think that this is a very nice work. I like the idea of the competition of 2 diseases, and it is very actual. So you have mentioned 2 possible case of studies, and I have liked to see application to see if there is a correlation with that data. But the main thing that came to my mind is due to the real situation of the pandemic, is if this model of two competition disease could be applied to the COVID and the influenza, because that, at least in Spain, is something that we are talking a lot. How we have known the disease in the previous period during the summer or spring, where the influenza was very low, and what is going to happen with the influenza or the flu now in autumn, where traditionally the cases of this disease increases. So how do you think it could be correlated? Because I think it could be a very interesting topic, and even also with the problem of pneumonia. That will be a case of 3 disease, or could be applied like 2, or it cannot have any relation with your models.
Yeah, well, thank you for your question. Well, actually, we are currently trying to work with this model, applying for the cases of the relation between meningococcal disease and influenza applied to the Australia data. We are working with some researchers from Australia to try to make fit in this model, because there are strong research that think that the relation between meningococcal and influenza is very strong. So if we can fit the model between using this interaction between diseases, we can define, for example, in this case, that we can make some vaccination decisions, for example, for influenza, in order to decrease the number of people of meningococcal disease. The same can be applied for any kind of interactive disease. If we can fit this model, for example, if we found a disease that can make some change in the behavior of COVID, for example, we can try to take some decisions in order to, for example, getting more people infected. Maybe supposedly, if influenza affect competitive COVID, for example, we can say, well, maybe influenza is not worse than COVID, so maybe it's better to get people infected from influenza, or maybe make people get vaccinated by influenza in order to get less people getting infected for COVID. So this interactive model can be applied for any kind of epidemic diseases that has an interactive behavior. So if we make the fit between both of them, we can take some decision from that kind. And actually, in the case of meningococcal disease and influenza, we are trying to make the fit in order to understand if we make some plan of vaccination from influenza, maybe we can decrease the number of people getting infected by meningococcal disease. So yes, it's possible to apply it to that. And we are trying to do it right now.
Okay, thank you. I found that would be very interested, because also you could control in one way, or just trying to suggest vaccination. Another question, well, that is related with this, that would be also that you have mentioned in the future line, to take into account the structure of the underlying network, because individuals are not flying in the air. They are on the air, and they have a lot of contact. So the effect of the social network will be very important to have it into account, no? And to consider different structures, for example, a more power law or random network. So I guess that you are also trying to apply this. That would be very difficult, or what is your idea about this? It would be straightforward to implement, or not so much?
Yeah, of course. Actually, for example, I will show you once again the state of art here. This one. The work that these researchers made was the following. They start with this model. In the homogeneous case, And from that model, they start asking themselves, what happened if we include the network? So they made some HMF approximation for the model, including the network. And they ask another thing, for example, what happened if you include the clustering in the network as a parameter? So we really want to make a similar path to try to understand not only the interaction between disease, but how the interaction between individuals can affect the behavior of each disease when you modify the temporal characteristic of disease. So yes, it's probably the next step in this case.
Okay, thank you.
Thanks to you.
Yes. Another thing is you have considered the unidirectional coupling. That means that you have one disease that is the driving and the other is influenced by that one. How straightforward will be to consider a bidirectional so that two diseases are more or less in the same way influencing one to another?
Yeah, that's right. So as you can see here in the set of differential equations, of course, because of the big number of differential equations, it's pretty complicated to try to make results and understand the results because of the number of different parameters that are included in this equation. So we started with the simpler case that is trying to just modify one of them and see what happens. So, but of course, because this model is made in sort of way that is possible to make a bidirectional disease, because you can modify gamma 1 int and beta 1 int and beta 2 int, so you can make all the combinations of interaction between disease. It is possible. So maybe we have to make more work in order to, maybe even more computational work to try to solve these numerical equations. Or maybe we can study some additional techniques to try to make some simplification that give us a general understanding that what can happen when you have two interactive diseases, bidirectional case.
No. Of course, I understand that there are many parameters and a lot of differential equations, so that's complex, but I was curious about that. So, okay, I think that's all. Thank you very much for your presentation. And I want to congratulate you and your advisor for a very nice piece of research that I think is very interesting. And what is more important is that it opens a lot of new research line that can be very successful. So thank you again for your presentation, that it was very clear and concise.
Thank you very much. Thanks to you.
Thanks, Rosa. So now I'd like to invite Professor Fujiwara to ask questions to Patricio.
First, so yeah, thank you very much for very nice talk. And not as a reviewer of the PhD, but as a collaborator, over this work. So I'm very proud that I could work with you. And actually, we have a lot of memory with this work that we work together. So I know most of the technical approach of this work. But let me give some comments. And first, you observe some results that if the time scale of the two diseases so similar to each other, the effect of one disease is bigger. In the both in the positive or negative sense. If so interaction is a cooperative, so the final size can be bigger, and if it is a competitive, the final size can be smaller. And in the case of COVID-19 and the influenza, that was asked. Well, maybe that kind of interaction can be not cooperative, but competitive. In that case, maybe such kind of interaction between diseases can decrease or reduce the COVID-19. So I believe that your result is very suggestive, and yeah, which also contains a lot of interesting implications to the current situation. And yeah, my question is about the novelty of this work.
Yeah.
Yeah.
Okay.
Yeah. So it is maybe for audience, but could you explain more about the novelty of this? Already did some extension to network case as a future problem.
Yeah. Sorry, I think that I lost you for a moment, so I couldn't hear you. Your question. Sorry.
Hi, can you hear me?
Yeah.
Hello.
Yeah.
Okay. Yeah. So yeah, I want to ask you about the novelty of this work. That so you have already you presented some previous work of multi-layer network case. But you told us the extension to the network case as for future work. So what is the difference between such kind of previous works and this your work?
Okay. So, well, even that all the previous work are very interesting and are the foundation about how we start to defining how we starting to make this research. None of the studies that we already know study the effect in the temporal characteristic when you have this kind of interaction. So the same goes, for example, sorry, let me go to the state part. To this case, that maybe it's one of the more general models that include interaction, and it's a very interesting piece of concept and research that include all the possible interaction, not only between two diseases, but with multiple diseases. So we will be very glad to try to include some kind of model with this shape in our model. So in order to include interaction between diseases, interaction between subjects, individuals, and so on. But none of the results given for any of the studies have been included the idea of how the temporal characteristics, in this case defined as the tau time, the peak time, as a result of the change in the behavior of disease. Because it's very important to understand that, of course, if you have interactive disease, if one disease increase or decrease the number of infected, that will affect the increase or decrease of the number of infected on the other disease. But it's also very interesting to try to understand and see if this disease appears earlier, for example, because of change of season or so on, maybe this disease will appear earlier too. So we have to take measures in order to prevent that situation. Or the opposite case, if this disease maybe appear earlier, this disease will appear later, so we have more time to make people getting safe, or I don't know. So that is the novelty of our work, including the temporal characteristic, and talk about faster or slower diseases in our research. I hope I answered your question.
Hello.
Hello. Yeah.
Hi. Okay.
Yeah. Maybe you didn't hear the last part, maybe?
The last part, right.
Okay, well, I just say that you can make some decisions, take some decision because of this interaction between behaviors, temporally talking about, between one disease and the other one. So I really hope that I answer your question. Yeah.
And yeah, so I'm so now also working with so public health people, and so they think that so interaction between diseases are really important. Yeah, so and so this so yeah timescale problem yeah should shed light on some so new yeah problem of interaction. Okay, thank you very much.
Thanks to you.
Okay, thank you. Now I'm also having some internet problems. I'm trying to switch to my 4G connection. So give me just. Hello, can you hear me? Yes, I think.
Yes.
Yeah,
Yeah.
sorry about that. So to continue from this section on questions from the committee, it is our tradition that the main supervisor is the last to ask questions. So it's my turn to ask questions before Werner. So thanks, Patricio, for your presentation. It's a very interesting topic. You have nice results. I have maybe some more basic questions first. I have lots of questions, so I'll do a selection of my questions.
Okay.
So could you please explain, because this is part of this is your PhD work, and you probably define some hypotheses and specific and general goals for your work during these years. Could you please comment on that? What was your main research questions? What were your objectives?
Well, the main research question was the one presented here in the presentation. That is, if temporal characteristic of one disease can affect the behavior of another when both of them are affecting the same population. So that was the main question here. So from that point, we start making some research. We start applying the model, making some research about what will be the best model that fits this kind of interaction that can be produced between diseases. And from that point, the specific goals on this research could be apply this kind of model, for example, as we told, in real data, to try to make some new insights about the interaction between diseases and how the temporal characteristics are made in this case. So yeah.
I also was wondering what were specifically your contributions in your thesis, which is related to, I think, to Professor Fujiwara questions. So what's the novelty? So you mentioned that the main contribution is this time domain characteristics. Is that right? Is that what?
Yeah, that's right. Yeah.
Okay.
It's not the main novelty. Yeah.
Okay. But then my question is, could you, because basically you did you did lots of numerical simulations. So you characterize the time characteristic by testing several different scenarios, I would call them.
Yeah.
So
yeah. It's just me, or I lost the.
Yeah.
Okay.
did you have a look at, can you results from the?
Sorry, we lost you for a moment.
You lost. Okay, so I was wondering if you can get some more analytical results from your.
Yeah, well, actually, one of the first attempts to try to get results from this model was try to get some analytical results from this. But actually, even for the SIR original model, is really complicated. Just in the last few years, there are analytic results for the SIR model. So we think that will be very interesting, even if we don't have the specific analytical result because of the complexity of the problem. But we are very interested in trying to make try to define some kind of approximation to the model, just in order to have general insights from the equations to maybe some simpler case. But yes, there are so many differential equations related in the work that it's really complicated to try to have an analytical result here.
Okay. But even usually you for this kind of system, sometimes you can get the final equilibrium point. I think what you call the prevalence number.
That's right. Mm-hmm.
So is that even possible for the simplest model?
I think so. I think that is possible. But well, in this moment we didn't make any advance in that area. But I think that is very possible to try to make some stabilization works in the model. Yeah, it's possible totally.
Okay. So another thing that I have some questions, especially in this time of COVID and looking for the vaccine, or even social distancing, as Rosa mentioned. So you can take measures. I mean, take actions on the spread of the disease. Yeah. So in your model, these actions, what would? Oh, I think my connection is still unstable. So actions in your model, in your parameters, you need to introduce an additional signal. How that has been done in the literature, or how do you think you can include it in your model?
The measures should be focused in change the parameters of the model. So that will be, maybe I can show you once I get the model. Here, okay. So these parameters here, I don't know if you, yeah, let's see. These parameters here, beta1 int, beta2 int, gamma2 1, gamma2 int, are the parameters that define the interaction, okay? So for example, if you can take measures in order to change those parameters, because, let me see, the gamma parameters, even that are modified because of the interaction, you can't take a lot of effort to trying to modify the gamma parameter, because the recovery time under normal circumstance is almost the same for all the people. So the focus should be in how the infection rate change in this case. So all the measures should be focused in change of course, the infection rate of the disease itself. Also, if we are talking about COVID, we should make social distance measures and so on to try to decrease the number of people getting infected directly from COVID. But if we found another disease that affect the behavior of the COVID, maybe we can try to affect the spreading rate of that from that disease in order to change the behavior of COVID in a positive way, of course. But yes, the focus should be in the beta parameters in this case. The change in the gamma parameters could be very difficult to make, really.
Okay, so in the beta you can put beta of time. You can change that.
That's right. Also.
Okay. That makes the problem much more interesting.
That's right.
yes, but of course, much more difficult.
Also,
okay,
yeah.
And my other question is related to you mentioned specifically which solver you used to do the simulation. So I was wondering, what are the numerical difficulties in your model? Because why not a standard Ranchkara solver to this set of equations?
Yeah, the model used here in the methodology here. Yeah, used here is because the LSODA, as I know at least, is a solver that can work with stiff and not stiff differential equations. So because we didn't know what kind of result we will have from the equations, in that case, we used the more general case possible in this case. That also was included in the Python library that I used for the evaluation of the model. But yeah, I studied what was going on behind the the function. So it makes sense to use this kind of solver, because we really didn't know if the solution of the equation will be a stiff or non-stiff solution. So that's the answer for that question.
Okay, but did you try a standard range kata solver? Or?
Not really, actually. Yeah. Okay. But it's supposed that this kind of solvers choose dynamically what will be the best form of solution to this kind of set of equations. Yeah. It's supposed. I am having a hope of faith here in the solver.
I was wondering because from the time, so from the results, numerical results you show, of course there are different time constants involved.
Yeah.
So it's not obvious for me to see what were the numerical difficulties.
That's right. That's right.
I was wondering if there was a special thing I was missing, maybe. Yeah. And I think I have one more question. Well, one thing that you mentioned in the document is that you're using a mean field model. But I missed an explanation. Where is and why do you need a mean field model for all this disease propagation? Could you
because
that explain more?
Of course. Behind these differential equations, because here, this is the model. So of course, this model itself is an approximation of a situation that is occurring in the underlying case. That is, for each interaction between individuals, there is a certain probability of getting infected or not. So behind this model, that is an approximation, because this doesn't have probabilities included here even explicitly, because behind it there is a probability model, and this is the approximation of that kind of model. In the SIR model, it's more clear that if you get in contact with a certain probability with a subject infected, you with certain probability will be infected or not from that individual. So we make the same approximation in this case, because try to work directly with the probability model in this case will be very much difficult in this case, and doesn't have more relevant result that we have here. So that's why we use this kind of model as a mean field approximation.
But does that mean that there's a map between your beta coefficients and a stochastic model or a Markov chain model?
Yeah, that's right. There is a correlation from all those parameters between this approximation and a stochastic model, as you said. That's right.
Okay. So it would be nice to see how you do that. I haven't seen it, so.
Yeah.
Okay. So I think that's those were my questions. So thanks a lot for your presentation, Patricio.
Thank you.
And now we have Werner. You have questions. It's your turn, please.
Thank you very much. I have well, I mean, I'm very proud for Patricio for her works. I'm very grateful also for having the opportunity to work in close collaboration with Professor Fujiwara. This collaboration started when I traveled to Japan in, I think it was 2016, was it?
Yeah, that's right.
Yeah, and I'm very happy this talk we have at the CSIS when we first met ended up here, and I hope we can continue this kind of collaboration in the future. Well, I just have one question, because most of you in the committee went through I think all the possible questions went to future work for applications for analytical analysis or etc. So I just would like to go a little bit further. One of Juan questions, Professor Yu's questions is regarding to stability. you set up a scenario where the one of the disease, D1, is independent of D2, and D2 is affected from D1. So it means that D1 is the stimulus, and you observe the reaction on D2. So the stimulus does not, you control the stimulus, and the stimulus does not change based on D2. When you have a scenario where you have the two ways interaction, meaning that D1, the stimulus, can be affected by the results of D1. So you may have like competitive case, for example, where that's pretty much like a positive feedback in a control setup, right? So what do you think are the challenges of analyzing these cases where you have two-way interactions, like full duplex?
Yeah. Well, including of course, the complexity of trying to solve that problem itself. More than challenging, I found that there could be a very interesting things that we could see in this model, because of course one thing that we can see is competition, as you said, but maybe actually this model can include a more interesting interaction. For example, competition in one way and cooperation in the other way. So can include this kind of weird interaction between diseases that can be produced maybe in real data that we can find. So the challenge itself is, as of course we said, is try to have a better insight in the equations, maybe try to make some approximation from the complexity of the problem, try to make an approximation, a simplification, in order to get general insights, at least that what is going on. And of course, the stability analysis in this case could be interesting in order to see what are the points that get constant in between models. But yeah, that is the most challenging, I think, that we can see in the use of the model when you have bidirectional interaction.
Yeah, thank you. I have another question is regarding that. It is very common in this area to use this kind of modeling for disease spreading process, but also to use in social networks for, let's say, fake news or memes or this kind of things, propagation. How do you think your model could be applied in this kind of different setup? This is one question. The second question is, let's say in a different kind of economical setup, when you have a kind of things happening in, let's say, in economic, like trade or things like that, some product gets, for example, more popular than other. And how do you think this work can be applied in a kind of different setup, social network or an economical process?
Well, actually, the SIR model, that is one of the most popular, if you want to say it that way, models to take the behavior of epidemic spreading disease. It is actually used in social network modeling, or, for example, as you said, in economical use. So, of course, it can be used. For example, you can start thinking about how the rumors start to spread in, for example, I know social network like Twitter, for example, and how the spreading from different rumors interact between them and produce that you will believe more in one rumor or in another, or the opposite way. So yeah, it's totally possible to use this kind of model in other situations that are not that explicitly related with the origin or the objective of this research. But yes, it's totally possible to use it. And it's used right now, this kind of models.
Okay, thank you. So I think that end my questions, but I would like to, after Professor Osorio question, if you can give me the word again, because I have questions from people in YouTube that would like to read to Patricio.
Okay.
Okay, yeah. As Berna suggested, I don't know if Felipe Osorio, Professor.
I would like to thanks for the invitation, and my question is from the statistical point of view. My only question is about with real data at hand, how to test the independence between or competition or cooperation between diseases.
Yeah, that is a very good question. One easy way to try to find that is just try to make the fit between the data and the model and see what's going on. If the parameters take us to the independence case, cooperation or competition, that will very first insight that maybe that is the kind of interaction that is producing here. But yeah, it will be very interesting to try to find another ways that can get insights about what kind of interaction are producing in the disease. For example, taking a look at the state of R, there are multiple research in the case of meningococcal and influenza disease, there exists interaction between them. So probably if you make some kind of fit and the fit is not correct and doesn't produce an interaction, it's probably the model not make a good fit in that case. So, but yeah, that will be a very first possibility, an easy possibility to make the relation between data and the model itself.
Okay, but just can I ask a little question?
Yeah.
When you say if we can fit, what do you mean about that? You fit about using real data or what is your meaning?
Yeah. Well, actually, right now, in the case of data from Australia, I don't remember what kind of algorithm I am using, so sorry about that. But we are trying to make the fit from the real data from influenza and meningococcal disease using the model. So the algorithm is just doing a search from what are the better parameters that fit better the data, the real data. So that's what's going on. So that is it's a possibility that we're trying to see if it works well or not.
Okay, thank you so much.
Thanks to you.
So thanks, Felipe, for the questions. So now, Werner, if you can get or you can detail the questions from YouTube.
Yeah, there is one question from William Luligo. I'm sorry if I'm not reading his name correctly. He said, congratulations, Patricio. Only one question. The data used in this work was from a public repository and the data was anonymized. This is one question. And then he has a comment. I have found a good article where it has used a SIR model harnessing cell phone traces to model the spread of Zika in Colombia from Enrique Frias et al. So that's the question. So was this data public or using this?
Well, actually, in this first research, we are not working directly with real data. So all the results here are evaluation from the model for selected parameters. So the next step is try to see if this model, as just said, fit well in a good way with real data. So yeah, those are only the evaluations from the model using selected parameters as an example of this working model. So there is no real data used in this work yet.
Okay,
yeah.
Thank you.
And thank you very much for the comment from the paper.
Hello.
Yeah.
Okay, so we need to go to the breakout room, I think. Okay. We'll back soon.
See you later.
Okay, see you.
Hola Patricio, me quería despedir, tengo después una reunión, así que muchas gracias por la presentación.
No, gracias a ti por asistir y por la pregunta.
Sí, y sí, bueno, sí, mis felicitaciones y felicitaciones también a tus profes guía. Muy, muy interesante el trabajo y quizás después podemos seguir en contacto ahí con tu profe. Así que, porque
Súper.
me invitó Werner, así que por eso estaba al tanto. Así que un abrazo, que te vaya muy bien, cuídate.
Muchísimas gracias igualmente. Y sí, me gustaría mantener el contacto, así que estaremos conversando.
Ok, chaito, cuídate.
Chao, chao.
Hola de nuevo.
Hola. Los esperaba.
Sí, we meet now, yeah. We meet now. Mi internet estaba más o menos, Patricio, por eso estaba sin video, así que si me dejan de escuchar, avisan.
Sí, no hay problema. No hay problema.
Is now yeah there?
I think so.
Okay. So as a president of the committee, it's my role to give you the feedback from our evaluation, both for the document and for the oral presentation. So these discussions are always very interesting because it's good to have great work as the work that you did, Patricio. So in that sense, the committee is very happy with your work. The problem that you address is not easy. You did a lot of work, and the way you presented today was really good, concise, and you answered properly to all the questions. We have suggestions for you to improve the document. In particular, a thesis has to have clearly stated what were your research questions, what were your hypotheses of your work, and also to declare what were the objectives, the goals that you achieved. And also it's good that you mentioned that you have an associated publication in a good journal. So that has to be in the thesis as well.
Okay, thank
probably
you.
in the introduction. So we strongly suggest you to improve that, and we explain, of course, Werner, the details how you can do it. So we need to give you a score both on the document and the presentation today. So the committee has decided to for the document to give you a 95%. And for the presentation today, we unanimously, of course, agree that you get the 100. So that gives you the 98% as a final mark for your work.
Thank you.
And congratulations, because now you become officially a PhD.
Thank you very much.
And I'd like to congratulate Werner, because you are his first PhD student, which is a great outcome. And we're happy for you also, Werner, and congratulations to both of you for these years of work together. So I think we can suggest to use the clapping here in Zoom. Of course, you can do it properly. And a big hug. And of course, I'd like to give also the committee the opportunity to say a few words.
Thank you very much.
Rosa or Maria?
Yeah. Well, how can I say? I'm kind of, yeah, very impressed. I'm very happy that, yeah, I can be here, and yeah, it's a really nice moment. Yeah, we have a lot of memories, and we will for sure have,
of course.
Yeah, a lot of so yeah, we can work further. Yeah, and yeah, I want to see you, yeah, physically. So yeah, when this COVID-19 issue is over, And
Excellent.
yeah, really, congratulations. And so let's, work further. Thank you very much.
Thanks to you, Professor. Thank you very much.
Congratulations, Patricio. I'm very happy to have been in your committee, and I wish you a lot of success, and I wish you that you follow on this work because it's very interesting, and you have I think that one of the great merit of this thesis is the potential. You have opened, you have many possibilities to do research and with an application. So congratulations, and I wish that you follow on that direction. And I wish you all the best in your future career. Enhorabuena.
Thank you. That's it. And thank you. Of course, I will go in further with this work. Thank you.
Excellent. Bernard?
Okay, Patricio.
You can cry now.
No. we will cry later with the...
Yeah, of course.
Well, it has been a number of years. Patricio, you also did the master's degree with me. On that occasion, we worked together with Rosa, and I had the opportunity to go to Spain, and we also published your research in a journal. So I think all the merits are on you. It's your hard work, it's your determination, it's your independence also for pursue the research topic by yourself. I think the merits that I have are very little, and I think it has been a tremendous pleasure and honor to work with you all this time. So I treasure this time, and I thank you for choosing me as your advisor. Thank you very much.
Thank you, Werner. So, well, if I can say a few words, of course, thanks to all the committee members for being here, for being receptive and appreciate the work that we're presented here. And of course, I want to especially thanks to Professor Fujiwara and of course my guide professor Bernard Keisel for all the patience for all the knowledge that I learned from both of you. So really, I will always remember how you helped me in some moments and what I learned from you. So thank you very much. And well, this part I will say it in Spanish because it's for my family. So esta parte la voy a decir en español para la gente que pueda estar viendo, mi familia, etcétera. Por supuesto, darle las gracias también a mi familia, a toda la gente que me ha apoyado, a mis amigos, y dedicarle esto a mi esposa y a mi hija, que son realmente los que me han llevado tan lejos. Entonces, sí, gracias. Gracias a ella. Eso.
Gracias, Patricio. Great job, Patricio. Well done. Thanks a lot. Yeah. I also here as a representative of the program. So for us, it's really good of our PhD program. I mean, it's really good. We are happy that we have another PhD graduated, and it's great that there are these links with the people overseas as Rosa and Naoya. So thanks very much for collaborating with us as a program, as a department, and I insist that this is great for. It's a good day for everybody, especially in this pandemic. So we will be at home working.
That's right.
But this is the part where Patricio is supposed to be thrown into the swimming pool at the university.
That's right.
So
that's right.
I'm not sure how we can replace that moment in Zoom, but at least Patricio,
give them some weather.
Yes, please have a glass of wine or a glass of beer because you deserve it. You deserve it, and we are happy for you and for the university and for everybody. Yeah, well done. Good job.
Thank you very much once again for all of you.
Yeah, sure. No problem. So that's finished my role as a president of the committee. Thanks again, Rosa. Thanks again, Naoya. Thanks, Werner, for inviting me to be part of the committee. And it's been a great experience for me again today. Yeah, that's my role.
Thank you, everybody. Yes.
Thank you.
very
Thank you, Juan, for being the president of this committee, and has been a pleasure to be here. Thanks to all of you. And Patricio, I hope that you, when time changes, you can visit again to us in Spain, in Madrid.
I really want.
And celebrate with all the group your PhD.
That will be awesome. Thank you.
Okay.
Okay. So
Bye bye. I
that's
think.
all. Enjoy your day. Enjoy your
Enjoy
day.
your day. Bye bye.
Thank you very much.
Yeah.
Bye.
Thanks a lot.
See you, all of you, later. Bye bye.
See you.
Bye.
See you.
Bye.